So, folks, one announcement is that EDA file, exploratory data analysis file, has become too big, and people are having difficulty viewing it. So, ignore that file now. I'll delete that. Instead, I've broken that file into two different files. One of them is called tabular data.pdf, and the other is called network science. At this moment, network science is very much a work in progress. You guys can watch it evolve, but we'll stay a little away from it. Focus on the tabular data. That is the standard structured data, machine learning on structured data. I have shared the links with all of you. If you have not received those documents or cannot view the documents, let me know. At this moment, those documents are evolving on a daily basis, right? Every 2 3 days, I keep putting a new version there, so newer content keeps showing up. Now, I'll just show you what is there in this document. We have, just to give you the things from the very beginning, you're familiar with this. At this particular moment, it is.
We can see your screen.
You can't. Okay. I thought I'd share. Okay, we'll share my screen all over again. There we go. Can you folks see my screen now?
Yeah.
Okay.
Yes.
Yes. So this document, tabular data, has 293 pages at this moment. Quite a bit of it you are familiar with. Let me give you the chapters of this. Uh, this has, for example, what are the chapters? The exploratory data analysis chapter, which is something I hope by now you have done all the exercises for. Next section of the book, part 2 of the book, is about regression and classification. In the last session, we did univariate linear regression. Today, we'll cover a lot of territory actually. We'll do nonlinear least squares and we'll do multivariate regression. Next Saturday, we'll do classification. So let us go to the linear models and try to uh, uh, cover our territory there. So if you go to univariate linear model, here we are. This is what we need to do. So we need to do these exercises, folks. So you take this data set. I've given the solutions in both R and Python. So this is just loading the data. All these data sets are available in GitHub. You all know it is mentioned in the resources at the very end. So please do these notebooks. And as you do it, take my help. Reach out to me and take my help. So this data set we talked about, we discussed last time, we talked about the residual analysis. Just to recap, we did all of this. We found that, just because you get good numbers in your summary of the model, it is not enough. You have to do the residual analysis just to see if there is any pattern in the residuals, whether the residuals show homoskedasticity or heteroskedasticity, and that is, or any other pattern in the data. And so that we did. We realized we needed a better model, a polynomial model, and a polynomial model was a good fit. Right? Then we took another data set, which sort of is, in hindsight, looks like a bell curve. This data set, again, we did direct linear model. It was a total disaster. Adjusted R square was 0.007. In other words, it was practically zero, no improvement. But then we did polynomial regression. In polynomial regression, it turns out that it is a good fit, but we do have one problem. We have this wagging tails, a lot of oscillations in the periphery. You see this oscillations in the periphery or the borders. That is the Runge phenomena. And when you see this, it gives you a hint that perhaps polynomial regression is not a good approximation to this, or not the right way. It's a good approximation, but it is perhaps not the right way to model this data set. There may be a better way to do that. Those better ways we'll learn in due course of time. In fact, today itself we'll learn. And there is a topic called regularization, which we will start with in the very workshop number 2, how to deal with situations like this. So, oh, by the way, one more thing. that Prachi mentioned, those of you who are going to take uh, ML200, please drop a word to Prachi. And I will open up the registration today itself. It will continue right after this workshop. There will be at most a 1 week break, which I will keep for people to have doubts. I mean, after I officially end this workshop, I'll keep 1 week. I will continue to hold just help sessions so that people take help with their labs. Right? For whole 1 week, 2 sessions will be just for help. And then right away, we'll go into ML200, intermediate data analysis. So we did this data set, right? I hope you guys have finished the first one. So this is the Python version of it. Uh, the best I would suggest is do it and then reach out to me as you need help. What we are going to do today is a different topic. We ask this question. We are approximating the data as polynomials. Right? For example, when we get this data set 2, we approximate it with a polynomial. But it's what if you can just stare at it and say, you know what? I know what mathematical function this looks like. It reminds me of something. Now, this phrase, it reminds me of something, is perhaps one of the most potent tools you have in machine learning, especially in univariate machine learning, because we can visualize the data very easily in 2 dimensions. It often gives you a hint on what the function could be, the generative function behind it, or the relationship could be. When you look at this relationship, it may remind you of trigonometric functions, sine wave, cosine, and so forth. So you might ask, why are we doing linear models when what we should really be doing is asking this question, what is the amplitude and what is the wavelength of this sine wave? Because if I can tell the amplitude and wavelength of the sine wave, I can essentially, I would have essentially characterized the relationship, the function. When you ask that question, when you say that it reminds me of something, and let me try if I can fit that function to this data, you are doing something called nonlinear least squares. In other words, you're going beyond linear. You're saying, here is a sine wave, for example. If you look at this, what is a sine wave? It is this equation. I hope, well, I made it too big. This is the equation of a sine wave, isn't it? A sine kx plus, and then of course the epsilon is the error term. Do you guys remember the sine function? Anyone remembers the sine function? The A here is the amplitude. K is the sort of, it's the wave number. It is the reciprocal of the wavelength times 2 pi. And X is, of course, the x-axis. Y is, therefore, A sine kx. Now, this usually happens, you infer it if you have some recollection of your mathematics, basic mathematics and algebra. If you remember, then it says, this is reminiscent of that. So this approach of nonlinear least squares, while it is very powerful, it is, I would say, optional. It's very powerful, optional. If you get it, it's great. If you don't get it, no harm done. We will, in machine learning, learn a lot of topics where, so that this approach of just guessing the function uh, is only one of them. But there is a pleasure in being able to guess it. And when you guess it, this thing, analysis becomes very straightforward. So, how does it become straightforward? Um, Let me explain what this function is. Here, I've explained A is the amplitude, K is the wavelength is associated with wavelength. It's called the wave number. We'll leave it. Now, both in R and in Python, there is a support for nonlinear least squares. It's actually one of the things that most machine learning books don't talk about, but it is one of the oldest tools in the arsenal and heavily used by physicists and applied mathematicians and so forth when they deal with data and they make the models. They fit models to the data, or functions to the data. Right? So let's see how it starts. The way it works is this. Are you guys able to see my screen? Sorry, fit with fit. Let me look at it one page at a time. Um, fit page. Let me, continuous mode, single page. Yes. Is the text quite clear and visible to you guys?
Yes, so for me it is.
Okay. So there is a library in R called NLS tools. There, what you do is you prepare a formula. You say, this is my guess. Y depends on A, or Y is a function of A times sine kx. Now, x and y are the data. A and k are the model parameters, the amplitude and the wave number. And therefore, the point of this machine learning exercise or this modeling exercise is just to find what would be the best A and the best k value. So here you prepare the formula. Sine wave is the formula. Then what do? You try to fit, you create a model with this data, A, like X and Y are given as data, of course. Then you say, let's go and model it using this formula. And you start with the initial guess for A and K. Those guesses may or may not be right, but it is worth having a guess. So you say A is equal to 1, K is equal to 1. Setting them to 1 is usually a pretty good guess in this situation. That is it. In 2 lines, you do this, and after that, the model is built, and then you can view it. And it's very powerful, guys, that you can build a nonlinear model in just 2 lines like this. The thing is, let's see how good it is. Once again, we say that A, it turns out, was approximately 1.32. That's good. And K was 0.99. Pretty good. The p values look good. The t value, is the t value good or bad? The t statistic here. Would anybody like to comment? Is the t statistics here good or bad? Remember, guys, I'd mentioned that t statistic or t value above 5 is generally beginning to look good. Yeah. Our t statistics above 10 is pretty good. Here, our t statistics or t value is 56 and 189, 190. Those are very, very good numbers. Now, in this, you can't have the null hypothesis. There is no concept of the R squared. But what you can do is you can see the correlation of y to y hat. How close is y to y hat? You know, the prediction and the reality, how closely correlated they are. It's important. The other thing that is worth observing is that um, if you look at the correlation matrix, it would be bad if A and K are mutually correlated or they're mutually dependent on each other. So what you want to do is in the correlation matrix, see that the off diagonal elements are small. Right? The principal diagonal is of course 1, 1. A is perfectly correlated with itself. K is perfectly correlated with itself. But A and K have barely 16% correlation. That sounds like noise, right? So low correlation across the parameters is a good thing. One other thing that you observe here is that this converged very fast. It just converged in 3 cycles. Usually when an algorithm converges in just 3 cycles or 3 iterations, it means that it is doing pretty good, right? And it found the right answer, and after that it wasn't budging from the right answer. It was 1 part in million, 1.96 or 2 parts in a million. Um, uh, the 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 variation from the right answer was this tiny bit after a little while. So it is a pretty good thing. Now, when we look at this value, it is beginning to look good, but let's see the residual plot analysis. Huh? First thing, how do the residual plots look? When we look at this, do you guys see any pattern in the residues? Is there any pronounced pattern in the residues, guys?
No.
No. So that is a good thing. Do we see very outlier residues? So remember, residuals should, if they have large outliers, that again becomes a a thing of concerns. Now, you remember that outliers are defined as anything beyond 3 standard deviations. So, in this picture, which is on the top right, you see that most of the residuals are below 2. So, in other words, there is not a single residual that seems to be beyond 2. So, nothing certainly beyond 3 or minus 3. And so, there are no outlier residuals either, which again is very good. Then you look at autocorrelation. Autocorrelation I've not explained, but let me explain. Autocorrelation is when a value is correlated with its own previous value. For example, if you keep on measuring temperature during a day and you take the temperature measurement every minute outside, yeah, under a tree or something like that, you would agree that the temperature at any given time, at noon, for example, would be highly correlated with temperature just before noon. 1 minute before noon, at 11:59, and the temperature at 11:59 would be very close to the temperature at 11:58. So a value is correlated with its previous values, and that is called autocorrelation. Now, autocorrelation in residuals is a bad thing. And so here is a plot of a residual value and the next residual value. So you're seeing the next versus the present value, and you don't want to see any relationship between these two. When you look at this, are you guys seeing any relationship? I hope this looks like noise. There's no pattern in these residuals, isn't it? There's no obvious autocorrelation. The next plot, and by the way, these are famous plots in linear regression. They're very important plots, and it is always worth finding these out whenever you do your analysis. This is the next plot, QQ plot it is called. At this moment, it's called the quantile plot of standardized residuals. What it means is that I'll just give you the intuition without going too much into the QQ plot. Basically, what you want is that this axis, this line that is there for the QQ plot, you want most of the data points, residual data points, or this quantile points, to be hugging this diagonal line. If it is not hugging, except for in the periphery, except in the corners, outer edges. In the outer edges, there will be some deviation, you can't help it. But if the bulk of it is hugging this line, it is a good situation. So if and when you contrast that with the QQ plot in a bad situation, then I believe in the previous chapter we had, it was not hugging the 40 this diagonal line at all. So in this one, it seems to be hugging the diagonal line pretty closely. This would be called a pretty good QQ plot. Yeah. So all of it confirms what? All of it confirms that our model is probably not wrong, isn't it? After residual analysis, what do we do? One final thing we do, we need to plot our prediction onto the model. Let us go and the same thing, we will plot our predictions onto the model. And when we do it, does it look like a good, faithful fit, guys? Would you say this is a pretty good fit? You look at this and you think, yes, this is a good fit.
Yes.
It's a pretty good fit. And now, instead of R squared, the best you can do is you can find a correlation between your prediction and the reality. Y hat is your prediction, Y is the reality, and it has an agreement of 98.5%, which is very good. Right? It's a very good thing. And so, the what did we learn from this exercise? So, what we learn is if you can guess what the underlying function is, what the generative force is, or the dynamics is, it is almost the gold standard. Right? It will beat anything. Its residual plots will beat your polynomial regression. It will beat anything in the linear model family. This really will take the cake. Right? Not only that, you have advanced understanding. When you say that what I'm seeing is a sine wave, something like this, yeah, you have actually said that I believe that the generative force or the laws behind this data are this equation. And so you have just discovered an equation that describes the data very well. And that is a very good thing. Are we together? Now, this is important, guys, because these days, and this is obviously a little bit going tangentially, one of the big debates in this field is, and you can't believe that it's happening, people are asking, do we still need science? Right? The concept being that today, the AI algorithms, the AI machinery of machine learning, the whole machine learning apparatus, can take data and can make very good predictions. Considering that it can make very good predictions, why do we need scientific theories at all? So one gentleman, Anderson, he wrote a fairly influential article once. I will forward you guys the article if it interests you. And it was really talked about, and it spoke essentially of the death of science, right, or the lack of need to do science at all. And it's an interesting perspective. I'll let you think about it. Then, obviously, a lot of people began to agree with it, right? And it became very fashionable to say that the new science is data science and all other sciences, forget about it. Then, not everybody agreed. People like me don't quite agree. We still believe that it is just not enough to make accurate predictions. You should understand why, what really is going on, what is the dynamics behind the data, what is the equation explaining the data. So the old way is, of course, you try to derive an equation or approximate it, and when you do that, you learn something. You learn something about nature, about the forces, or about the financial markets or biological systems or whatever, right? So and again, people disagree. So one of the lovely books that recently came out was called The AI Delusion. It sort of deconstructs this whole belief that all you need is prediction models and you don't need science. And I'll let you guys form your own opinions if you want to Google that up and check it out about this. But these things have profound implications, guys. Do we build only models that predict, or do we want explainable machine learning? A machine learning that we can explain as human beings. We can say, this is the reason why. Or we believe this is a hypothesis which is explainable with the equation or with something. And is that even needed? I fall into the camp which is strongly in favor of explainable AI. A lot of people feel and have been feeling for the last 10 years, many years, that explainability is nonsense. All we need is good predictions. Right? So you can form your own opinion. You can read all these articles. And there are people who are halfway between. It's a whole spectrum of beliefs. You can think about it. But as we move along, I will emphasize interpretability and explainability of our machine learning models very highly. It is also important from a legal perspective. Let us say that you have an algorithm that hires people, right? It gives them a test of a barrage of questions, 100 questions, and based on how they answer those questions, it goes and associates scores with them, makes a machine learning model, and it predicts whether they would be good employees or not, right? Or competent, high performing employees or not. If you build a model that cannot be explained, that is a black box, the problem with the black box is, how do you know that it is not discriminating against any of the protected classes? For example, it's not discriminating against the blacks or the Indians or the Asians or the Hispanics and so on and so forth in the United States, or against the whites. You don't know. You don't know whether it has a gender bias, whether it has a bias against disabled people. And these biases are very subtle. Quite often, in the words we use, our biases show. There are tools that will tell you whether the paragraph that you wrote has a strong male gender tone, or it has a strong female gender tone. And these things are effective in our responses to them. Right? And so it would be worth knowing that, did you reject this person simply because the paragraph that the person wrote overall had a female gender bias, but the machine could not explain it? It just went for the fact that it likes people with a strong male tone. or something like that. It could be, I'm just giving a hypothetical situation. Increasingly, it has happened that as people are studying a bias in machine learning models, it has become a huge issue. We are discovering more and more that these black box models are a huge problem. They are a huge problem uh, when it comes to bias. And we really need to watch out, right? It's a very this is a very powerful tool. If you don't use it carefully, it can be very dangerous. So interpretability and explainability is one of the core things that helps you understand whether your system does or does not have biases, right? Because your underlying data may have bias that it has learned from, and biases are often very subtle, which is why they are sort of discovered a posteriori. You build a model, you unleash it onto the world, it does its damage, and then somebody notices, some researcher notices that it's having an adverse impact on protected classes. So one has to watch out for that. Now I'm going to do the same analysis in Python, not very different. All of these, by the way, guys, do you notice that this entire modeling was just 3, 4 lines of code? You include this library, 2 lines, 3 lines of code here. That is it. And to generate the residual plots, again, 2 lines. 5 lines produces your complete analysis. This speaks to the power of this modern machine learning tools, whether in R or Python, how absolutely powerful and elegant it is. Or try doing it in a low level language like C, C++, Java, or whatever it is, and you'll realize how difficult or how much of territory you would have to cover to create something like this. It's a long journey. Well, uh, it's a lot of code. It will be a few hundred lines of code. Right? So that way, get used to these libraries, guys. Machine learning is not so much about coding as about understanding, because the code is very, very small always. The same thing we do it in Python. We write the equation. In the Python version, I also added one more extra term. It's called the phase lag. Y is a sine kx plus phi. Right? One more parameter we added. So now it is a 3 parameter model. Once again, what we do is we define the sine wave here uh, to be this, right? It is a times sine kx plus phi. If you compare it to this equation, y is equal to a sine kx, you'll realize that all I am doing is quite literally writing the same thing in code in this particular line. Do you see this, guys? The line that I have highlighted is exactly the same as equation 2.4. That way, both R and Python in this respect are very, very expressive, except for the star and the word np dot this thing. It looks almost verbatim the math. I hope you can see the simplicity of this, guys, how simple it is. And so if I were to zoom out, if I were to again start with some initial guesses, and then I say go and fit the curve, right? It will fit this data. And once you have that, what are the things that we want to find out? K, phi, and A. Right? Now, this is just some pretty printing options. When you print the thing, a standard Python, I could have just printed the value as it is, but then it would be to many arbitrary decimal places. It looks a bit ugly. We don't want to print so many decimal places. So Python gives you a way in which you can set the printing options. You can say that for floating point numbers, for numerical values, use a precision of 5. And this is standard string formatting syntax. Those of you who are used to it can use it. See, it is not necessary. You can just say print A or print K. That would have been good enough. But if you are not used to the fact that in Python you can pretty print text quite well, this kind of a syntax, curly brace, colon, less than 5, and so forth. What you're basically saying is that the first one limited to a precision of 5, right? That sort of thing. And for all of them, the three of them. So now, at the same time, this returns you two objects. One is the parameters, the value of the parameters. And the second is it returns a call called parameter covariance matrix. Are they correlated? Very much similar to R. So what are the values of the parameters? A is 1.32, K is 1, and phi is close to 0 practically, which is exactly what we found in the R code. Are we together? By the way, guys, I am holding out on giving you the solution notebooks, the Python notebook with the solution and the R notebook with the solution, simply to give you guys time to work on these labs yourself before I release solutions. Let me know. I'll eventually release all these solutions. But when you guys have all done the lab, or tried to do the lab on your own, let me know. Then I'll release the solutions. Just as I release the solutions for the exploratory data analysis, I'll release the solutions here also. So we can see the covariance matrix. Once again, it's mostly filled with zeros, which is absolutely lovely. Zeros. Now, in Python, it turns out that things like the confidence interval, etc., are not computed on your own. So you have to sit down and compute it yourself. So how do you compute it? You go and open the ISLR book. You look at the definition of the confidence interval, how is confidence interval um, defined, and then you write it up as code. As simple as that. And you can do that, though I would say that not necessary. Most people these days they don't worry too much about confidence intervals. I mean, it is a good thing to do that. People often skip it. The Bayesians, of course, believe that it shouldn't be the confidence interval. It is misleading. Right? But one way or the other, the 95% confidence intervals are pretty good. So what is the last thing we want to do? We want to also create a correlation. I mean, the scatter plot between y and y hat, right? Are they correlated or not? So we get this plot. Would you say y and y hat have a very strong correlation, guys? Strong positive correlation? Again, 98.5% correlation. Very strongly correlated. Means we seem to be heading towards a good model. So far, nothing is saying it's bad. Let's look at the residuals plot. Once again, if you're doing it in Python, you'll have to create it on your own. Residuals are nothing but y minus y hat, and so we can create a scatter plot of y hat against residuals. Do we see a pattern here? No, we don't see a pattern here. This looks pretty good. There is no anything, for example, there is no heteroskedasticity here in this model. Looks good. And then finally, we plot the predictions against the data. And when you plot the predictions against the data, it's again a pleasant thing to see that the agreement is pretty high. It's a high fidelity model. Would you agree, guys, that it's a pretty high fidelity model that we are looking at? Isn't it? Maroon line is the actual model, and these green and blues are the confidence intervals. So far, so good, guys. That's that. And this is the code. Like plotting code is always a little bit more than the actual machine learning code. It's one of the things you'll realize that in data science, there are two aspects. One is the machine learning itself, and that generally the code is very sparse. It's pretty brief, and quickly you get to the result. But then when you try to visualize the data, then art comes in, and art is always verbose because you try to make the plot look, aesthetically pleasing. You want to give it some good colors, axis, this, that, and so you end up writing very straightforward code that you have to get used to. You have to learn Python enough to create pretty plots. And actually, the plotting code tends to be a little longer and more complex than the actual machine learning code itself, which tends to be very straightforward in general. Whether you're doing deep learning or you're doing simple, linear models as we are doing, generally machine learning code is very, very short. Right? So, because the subject is not about code, it is about understanding data and how do you approach data and learn from it. All right, guys. So that was that example on nonlinear least squares. What I would like to do now is just talk about this thing, right? Uh, about R versus Python. So I'll read out. It's this thing. You may or may not have read it. I'll just read out this paragraph that I wrote. See, in repeating the nonlinear least squares curve fitting, once in R and next time in Python, we observe the close parallels between the R and Python code. As we have seen in the previous labs too, this is a recurring similarity. in general, once you have become familiar with the syntaxes of the two languages, translating data analysis code written in one of the languages into the other becomes more often than not a straightforward exercise. The exceptions to this are those cases where support for an algorithm happens to be in one of the languages itself. So, for example, there's a new algorithm, and the creator of the algorithm has just written a Python library only for it. Then, well, of course, you better go and use Python because there is no R equivalent. Or there are quite a few libraries at this moment still which are done in R and they don't have a Python equivalent. People haven't gotten the time to translate or create an equivalent in Python. And so you have to go and use R. It's a fact of life. Huh? So, in order to develop fluency with data analysis in both of the languages, it is instructive to repeat the lab exercises in both. Simplicity is in the eyes of the beholder. For common data science tasks, there is brevity in R code. And if you believe that brevity is the soul of wit and has more simplicity, then R code will certainly appeal to you. Those not familiar with it, on the other hand, tend to gravitate towards Python since it is a general purpose language in widespread contemporary use for all sorts of programming situations. Therefore, it is often the case that many have past fluency with Python, which makes it easier for them to analyze data using Python libraries, despite the resulting code being quite often a bit longer. You guys saw that, right? Python code tends to be a little bit more verbose, a bit longer. R code is, once you master it, it is almost exemplary in how brief it is and how much it achieves in just a couple of statements. But the downside of Python is you have to learn Python, whereas most people already know Python. I mean, sorry, if for downside of R is you have to learn R, whereas for Python, uh, most people already know Python. So they ask the question, why bother learning a new language when I already know Python and I can do machine learning in Python? Well, I would highly encourage you to learn both. R is pretty elegant language, um, and the libraries in that are very, very elegant. And of course, we have been seeing examples of that in the exploratory data analysis chapter. There were excellent libraries in R, and there were excellent libraries in Python. So pick up both. Since both of these languages are in widespread use and each can be learned without excessive effort, the author would strongly urge the reader to ensure that she um, comes to be fluent in both. When a data scientist describes either a new algorithm or the results of an extensive data investigation, it is customary for her to show the analysis details as code snippets written in only one of the two languages. Whichever happens to be the data scientist's favorite language becomes her language of analysis. It is assumed that the reader would be familiar with it. The community is broadly split in equal measures between the two languages. Therefore, not knowing one of the languages becomes a significant impediment to understanding the work of the other practitioners in the field. There will be quite a few significant books and articles that you will struggle to understand if you happen to know only one of the languages and the analysis is expressed in the other. Right? So that's the thing. And more informally, Murphy's Law will kick in. Rest assured that the moment you hear of something, some very exciting development in machine learning, and you want to go and read the paper or the article on that particular topic, invariably it will turn out that it will be the code examples will be in the language you don't know. So if you happen to be a R expert, you will stumble across good research that you really want to understand, but it will be done in Python. And if you only know Python, sooner or later what will happen is you'll come across excellent articles that you want to master, techniques and libraries, and it will turn out that the only coverage for that is in R. Right? So you should know both. And the code is so similar between the two languages. They're so close when it comes to data science. There is no reason not to know both. I hope that is one lesson I have been emphasizing to both of you, to you guys. Huh? Now let's look at this other example we did with sine wave. You look at this data. What does your instinct tell you? What am I looking at? Now, if you're familiar with curves, you would say, this to me looks like a bell curve, approximately. Would you guys agree that this sort of looks like a bell curve? If you say that it is a bell curve, then why are we approximating it with a linear or polynomial model? Because when we build a polynomial model, if you recall, what you end up with is the Runge phenomena or the wagging tail. So there's oscillations in the peripheries, not a good thing, right? So polynomial regression has its demerits. So the question is, can we do better than that? We can do nonlinear model. We say, hey, it is to me looks like a bell curve. These are the different shapes of a bell curve. And in a bell curve, there are only two parameters. One is the mu, where is the tippy tip hilltop of a bell curve, or the center of the bell curve. It is given by mu. People call it the mean of the bell curve, mean value, which is the center. And the other is the variance. How spread out is the bell curve? So let's observe this. This green bell curve, where is the center of it? It is at -2, right? And what is the variance? Well, it seems to have a pretty significant variance. It's a little bit spread out compared to some other ones. So this is it. Green one is centered at -2 and it has some variance. Contrast that with the blue one, which is positioned at 0. But how much is the variance? It's very low. It means it's very peaked at the center, as opposed to, let us say, the yellow one. Yellow one is also centered at 0, but see how spread out it is. It is uh, you have to go pretty far before you get to most of the bell curve, and so the variance is 5. That's the intuition of a bell curve. Bell curves are more formally called normal distributions, and their multidimensional representations are usually called a bell hill informally, but the more formal term would be again normal distributions or Gaussian distributions. Okay. So and I would encourage you, when you have these words, normal distribution, etc., have one word, a formal word in your mind. And also, I tend to find it easier if I have some very intuitive or may not be perfectly accurate, but sort of very intuitive name that is evocative. A bell curve is very evocative, of what the shape of the curve is. You'll remember it much more. So, what does a bell curve look like? Oh, goodness. Bell curve is a transcendental function. And why it is written like this. Right? There's an amplitude part, of course, how high the bell curve is. It is written in terms of mu and sigma. This equation looks complex, and the nature of transcendental functions is they do tend to look complex. However, if you remember from the lecture notes, I explained what these things are. Huh? It is x squared, what it says, right? Mean and sigma. So I'll leave it. Amazing thing is, while the equation looks so complex, the code looks exactly the same, almost no change. See, what did we do? We wrote a formula, the same formula, we converted to this. Here, you notice that we did that. And the rest of the code is exactly the same. We build an NLS model with this formula. We make initial guess for the values. 111 is pretty good to start with. Why not? Right. And sorry, in a moment, we have a model. That model once again looks good. The t values are very good, 84, 60, 72. The p values look good, right? And the confidence intervals are pretty tight, right? It says that a is between 0.95 and 1, which is a pretty tight value. The correlation matrix, again, the off diagonal elements are not very strong, right? Though little small values are there. Then what do? We go and look at the y versus y hat plot, prediction versus reality plot. And when we do that, it seems to be having an even better correlation. Do you see 99% correlation? Now remember, guys, even with polynomial regression, we did not achieve such a high degree of correlation between y and y hat. So this model trumps even the polynomial regression that we made. Now let's look at the residuals. How do the residuals look like? So there is again the same function. You look at the residuals. Are you guys seeing any pattern in the residuals here? Not much of a pattern. You don't see heteroscedasticity or anything here. Do you have outliers in the residuals? No, it is between -2 and 2. Remember, outliers are beyond 3 or -3. Right? You don't see that. Likewise, autocorrelation. Do you see any autocorrelation? No, this looks like noise. Pretty good. What about the QQ plot? Well, the data seems to be hugging the diagonal axis for most of the places, right? Except that it's flying off at the very end, which you expect. So, all things considered, is beginning to look not wrong, right? Let's see where we are, or at least it seems to be somewhat. It's an effective model. I wouldn't say not wrong, but it's an effective model. Now, let's plot the model against data. Do you guys see what a neat graph you get? How lovely it looks. It is way better than what you got with polynomial regression. So for example, let's look at the graph that you got with polynomial regression. This is the graph you got with polynomial regression. Do you see that it has a problem of oscillations in the end? Do you see that, guys? You have these oscillations in the end, right?
Yes.
Yes. Whereas when you look at this new graph that you have, it is, I mean, this is what you would call a beautiful model, right? Completely nice, smooth curve with no unnecessary oscillations at all. Right? And that is when you feel that you have done a good job in modeling this data. Right? And remember, where did we start with this data? When we started with a naive linear model, it was a complete disaster. Our R square was zero, practically, like 0.007 or something like that, which essentially, when you get a value like that, you throw in the towel. So systematically, by using better techniques, we have now ended up with a model which, from having no predictive power to such a high predictive power now, such a good model. Right? Which again speaks to the fact that when you deal with data and you're not getting results, it may not be so much in the beginning because there is no signal, but it may to a large extent be because you're not looking at the data in the right way. Behind data, there is always a generative force. It is quite possible that the predictor has nothing to do with, or the target has nothing to do with the predictor, the null hypothesis. But generally, if the data has, if you believe there is truly a relationship, you should make every effort to try to build as good a model as possible. If, in spite of all your best efforts, you still can't build it, then you begin to suspect if the null hypothesis is true. Namely, there is truly no relationship between input and output. So that's that. Now I'll redo this thing in Python. Once again, this is the equation. How do you do that in Python? Again, just a few lines of code. This is it. You define the function and then you pass it to the curve fit, very similar. As you can see, Python code is much more verbose. There we could do it in 2 lines. In Python, you have to write, frankly, much more code to make the whole thing work, but not too much code. It's just still fairly reasonable. And when you do that, it works. Let's see if it works. The same results are achieved, pretty good value. Right? I won't go more into it. I haven't plotted it and so forth because it seems redundant at this point. We are getting the same level of you know correlation. Likewise, we go and visit dataset 5. Dataset 5 is like this. It's an interesting dataset. You ask yourself, what does this dataset remind me of? And by now, remember, the question in nonlinear least square is this: what does it remind you of? So you might ask this question: how in the world would I know? What does it remind me of? The way to that is, generally you have to become friends with a lot of functions. I would like to illustrate this with a story. Uh, at one time, there was a problem posed in Europe by the Bernoulli brothers. Right? There were two brothers called the Bernoullis, and am I talking about the Bernoullis? I think so. Okay, the two Bernoulli brothers. Or I hope I'm not conflating it with another mathematician brothers. But anyway, so imagine there are two brothers, which I believe were the Bernoulli brothers. Now the trouble is they were both brilliant, but people didn't know that there were two of them. And so they would write some great mathematical result, and then praise may accidentally, half the praise may go to the other brother. or credit may go to the other brother, because people used to keep getting confused between these two brothers. And to make matters worse, they even had a nephew who too was a great mathematician after some time. And so after a little while, people got completely lost. Which of the brothers are we really, which of the people, three mathematicians, are we really talking about? So it again speaks, most people didn't even know that there were three of them, right? We only know the last name and we remember that. If we know their names at all. Now, what used to happen is between the brothers, there used to be a pretty healthy rivalry. So they used to pose puzzles at each other for the other to solve. They used to challenge each other. So one of the challenges they threw was an interesting mathematical challenge. I won't go into it. It's about how fast can a body fall? What is the best path for a body to fall from place A to place B, where A is higher than a B, but not directly above it. So, what is the fastest path, and so on and so forth? So, shortest time path, and so forth. So, that puzzle was interesting, and a lot of people got interested. They started trying to solve it. Then Newton heard of it. Newton obviously was very competitive of the European mathematicians. He used to just dismiss them as not to be taken seriously. So when he heard about the puzzle, he got interested. Except that publicly he was saying, this is nonsense. So then people submitted the solutions, and one solution came, which was very elegant. And was it Jacobi brothers, by the way? Bernoulli, I keep saying. Maybe it's not Bernoulli, it's the Jacobi brothers. Anyway, we need to go back and look at the history. I might be completely mixing up the names. But okay, let's take Jacobi brothers maybe. So when he looked at the solution, he immediately said something famous. He said, "You can always recognize a tiger by its claws." Right? And what he meant is he could recognize the genius of Newton in the solution that was presented. It Even though Newton's name was not attached, it was obvious that it is that genius who has submitted the solution. And it's a classic statement in history. And I like to refer to it because it's something like that. These functions that you see in mathematics, they are not just dull facts. They are elegant, they're beautiful, they're marvelous, they are like just, I mean, absolutely marvelous and beautiful functions. And if you could just take one family of functions, let's say here the gamma distribution, and just say that this month, I'll just look up the Wikipedia article, I'll read up a little bit, give half an hour, 1 hour to understanding what that function is, so that you remember it. You will be quite surprised by the time the year ends, you would know 12 families of functions. And so you will see them all around you. It becomes very interesting when, as a mathematician, you're just going for a walk. All around you in nature, you will find those functions uh, literally in front of you, written large on the landscape. And it's sort of um, as a child, I used to always wonder, will I be able to understand the world? What does it all mean? What is it behind all of this? What's the feeling of it? That's what brought me to science. And I must say that uh, the mathematics behind physics and behind computer science and behind artificial intelligence is sort of the core of it. I mean, it's sort of it gives you a very deep understanding not just of the individual subjects but of nature foundationally itself. It's very elegant. Somebody wisely said, I think it was Einstein, but I may again be mixing up the name, when he said that when I look at mathematics, when I look at these things, I can read the mind of God. You know, the God is essentially a mathematician. The whole world has a mathematical foundation. Why does it have? Nobody knows. It need not have. It need not be explained by mathematics. But as you see the world and you try to look behind, under the covers of what is it, how is it held together, how does it work, you always find beautiful mathematics there. And these gamma functions, again, like all of this, you see, if you can spot the function and say, here is the day, here is what I believe is really going on, you will do far more powerful machine learning than most people can dream of. Yeah. You can actually walk into a room where people are struggling, sit down, write an equation, quickly write code, fit a model to that, and have people occasionally, not always, but occasionally when it works, you can have people absolutely amazed. It feels as though you just pulled a rabbit out of your hat, because they may have been trying using all the traditional tools and they would never have thought to think about it more abstractly. So there's a value in that, guys. Which is why I'm explaining these things to you. So there is such a thing as a gamma function. It has two parameters, k and theta. So you can see that when k is very high, which is the black line, it almost looks like a bell curve. Theta is small. When k is low and theta is big, it is more like it completely looks like a reciprocal distribution. Then in between stages are there. This k is equal to 2 and theta is equal to 2 makes it look a little bit like a log normal distribution, skewed bell curve, and so on and so forth. You see these distributions. So when you look at this, guys, does it remind you of this? Would you say that if you knew the curves on the right and you look at data on the left, your first reaction would be, aha, I might know, I might be recognizing the tiger by its claws, I might be recognizing an old friend here. Would you say that? Look at the curve on the left, and would you say that it has a close resemblance to the curve on the right? Anyone, guys?
Mostly with the value k equals to 2 and theta equals to 2.0.
Yeah, that's right. It begins to look quite similar, and at the end of the day, you're just guessing,
Yeah.
But this is how this field works. You hypothesize. You say, okay, let me try this and see if it works. Remember, guys, in machine learning, you don't. There is no such thing as the right answer. There's only such a thing as an effective model that makes good predictions. So let's try that. Now, the gamma function, you'll have to open a book and see, now, what is the equation of a gamma function? Well, you don't need to. It turns out that the libraries, for example, this Python library, it already comes with a gamma function built in. Right? So I defined a function called gamma like, because I also put amplitude part there, gamma like. That's all. The gamma function, I multiplied it with the amplitude. Once I do that, I took the input and did that. This is again the formula. Rest of the code is exactly the same. All you have to do is use this gamma function and then ask the system to fit the values and see what it produces. Oh, it produces immediately a value of k is equal to 10, a is equal to 2, b is equal to a and b. So what does that mean? Right? Let's go and see what it means. K is the amplitude, so we can ignore it. And so it is saying A and B are 2, 2. Let's go and look at this graph and look at 2, 2. Where is 2, 2? Yeah. Is it the green line? 2 and 2 are the green line, isn't it, guys? This green thing is this. Now, I'll let you compare and see, is this green line a close approximation to your data? Would you guys say that it is? Guys, are you there?
Yes.
Yes.
Yeah, it does seem, right? It's pretty close approximation. And so you say, voila, you got it. So nice. And you look at the correlation matrix, everything. What is the correlation between y and y hat? A perfect correlation. I mean, it can't get better than that. Well, it turns out that this data set is unusual because when I was preparing it, I forgot to add noise. There's always noise in the data. I was trying to illustrate the point, and so I did not add noise. Because there is no noise, because this data is pure signal, obviously the correlation is 100%. So you have literally hit the nail on the head, absolutely on the head. You have hit the nail. Right? Let's try to impose our plot our model on the data, and we plot it. Look at this. Do you see a perfect match between the model and the data? Isn't it, guys? Oh, by the way, it is not bell curve residuals. It should be okay. The legends are wrong. Right? It is not this. It is a match of prediction versus data. What do you say, guys? See, when you there are occasionally situations like this that you will be struggling. If you remember, linear regression was a disaster. Polynomial regression worked, but it has Runge phenomenon, right? It had oscillations and so forth. It sort of worked, but when you make a guess like this, and you end up hitting the nail squarely on the head, it is exhilarating. It's just absolute pleasure to look at a data that you didn't understand just a couple of hours ago, and to reach a point at which you feel that you really found out what's happening. Now you say, why in the world would I worry about gamma functions and things like that? But these things, the sine wave, the bell curve, the gamma function, they all have one thing in common. Can you guys tell what is common to the sine wave, the bell curve, and the gamma function? Anyone? These are called transcendental functions. Transcendental functions are functions that cannot be represented as polynomials of finite degrees, polynomial or third, fourth, fifth degrees or something like that. If you try to expand it in polynomials, it will have infinitely many terms, which is the real reason why you have the Runge phenomena, those oscillations, when you try to do it. By nature, transcendental functions cannot be represented as polynomial. Now you say, well, so what? Why are they so important? It turns out that transcendental functions, to a large extent, is the alphabet in which much of the world is written. You go back and look at the equations, the quantum equations of electron clouds around the atom, around the core, and you will realize that what's happening. Are people dropping off? Uh,
Asif, we seem to have some network issues.
Okay. Is there anybody here in the meeting at this particular moment? Have we lost everybody?
I think most of them.
No, I can hear you. We can hear yourself.
Oh, you guys can hear. And you can see my screen also?
Yes.
Okay. Guys, in between, do keep giving me some feedback. Anyway, what I was saying, and this is a purely personal perspective. Today, I'm giving you a lot of my personal perspective or how I look at the world. To me, so one second, let me. And I've got a quick demonstration here about what I've always wanted to be a teacher. Goodness. I've been teaching. Yeah. So to me, these transcendental functions are like the alphabet, the language in which much of nature and dynamics and anything you do, even the financial markets or man-made things, any piece of engineering, if you ever model it, very, very often you'll find that your model will contain, your theories will be nothing but will be made up of transcendental functions. Think about it. You drop a pebble in the water. What do you get? You get ripples. Those ripples are sine waves, right? Those are trigonometric functions, circular sine waves going spreading out those ripples. You can see that they have troughs and crests and troughs and crests. Now you also notice that the amplitude of that keeps decaying with distance. That too is a transcendental function. I believe it's Legendre function, right? The drum you play are again given by transcendental functions. I'll let you discover which one. The the electron cloud that is around the core of an atom, the all of life is described by orbital structure and chemistry, right? And biochemistry. That orbital structure, the SPDFs, etc., those are actually the notes of a spherical harmonics. Those are the spherical harmonics of yet another transcendental function called the Bessel's function. So if you master transcendental functions, just pick one a month. You'll be surprised that you can enter so many areas of science and engineering and biology and chemistry and find yourself in familiar territory. You can look at what people consider the hardest part, the math of it, and to you, it will look very familiar. It will look very easy to grapple with and learn. Right? So it's a very powerful thing, and I won't say more about it, but that is it. So that is the context of transcendental functions. So, guys, I would like to take a small break, and then I would like to move on to real life data sets and examples, multivariate. let's take a 10-15 minute break. So here's the thing, before I take a break, guys, do you want to call it a day, like keep the nonlinear this data sets, real world data sets for next week, or would you rather that we do it today? Any voices?
Uh, Asif, I would want to take like do it next week. So
Next week, huh?
personally,
Okay.
Next week, sir. Let's do it next
Next
week.
week.
Next week is okay.
Okay, guys, huh? This has already been quite some time. We have been talking for more than an hour and a half. So it's all right. I'll stop the recording. Before I stop it, guys, I hope what you guys were all unusually quiet, and I can't see you. So I'm not getting any visual clues or audio clues on whether you're understanding it or not. Can you guys tell me, is it clear? Are you guys understanding this lab? The code will take some time to digest, right? You'll have to repeat the code, look up some documentation. But the foundational concept that you can guess a function and then try it out and see if it describes your data by do parameter fitting. That's the core idea. Are you getting that idea?
Yes, sir.
Okay, very good. So with that, I'll just stop the recording, guys. And obviously, I'll post this recording to the YouTube right after this. Let me stop the recording.